Okay, I'm home right now and my kids are in the other room watching, quote, educational videos. As long as they're quiet, I don't care. No, just kidding. So we're going to be continuing section 8.1 and I'm going to give you a chance to attempt a couple of problems that are similar to the ones that you saw on the handout. So here we go. First question that I have for you is regarding the angular velocity. So here's the question. What is the angular velocity of any second hand on a clock? Whether this is on a watch or whether it's on Big Ben, the angular velocity is going to be the same because it completes its 360 rotation in the same amount of time. So it's not dependent upon the size. The actual velocity, or the linear velocity, will differ depending upon the size of the radius, but the actual rotational angular velocity will not change. Okay, so what I'd like you to do is try to figure this out. Calculate, using the formula, what is the angular velocity. I'd like you to pause now and try to attempt to solve this, and then come back, and I'm going to pause here for a few seconds. Okay, hopefully you've attempted this problem and you're using this formula. You're able to pause this at any time if you wish to think you can finish this. So it is going to be the change of the angle over the change in time. So what we have is, this is, again, the second hand is going around a clock, which means that it's going around one circumference. And what's going to be the time period of that? So one circumference is going to be equal to the 2 pi radians. And the time is going to be 60 seconds. And if you take this 2 times pi and divide it by 60 on your calculators, you should get 0.105. And the units are going to be radians per second. Those are the units of angular velocity. So here's another question for you. Let's say that this is going to be from our clock that is in the room, and the room again has a radius of 10 centimeters. What is the actual velocity of this going to be? So we have the tip of the clock. This is looking at the second hand now. The tip of the clock, the radius is equal to 10.0 centimeters. What is the linear velocity of that? So we go ahead and try to attempt that problem. Okay, hopefully you finish this, and now we're going to be coming back to the formula. The formula for linear velocity is going to be depending upon the radius times the angular velocity. So the radius is going to be 10 centimeters, but we need to convert the centimeters into meters. So we have the 10.0 centimeters, and if we convert this into meters, 100 centimeters is equal to 1 meter. Because velocity is measured in meters per second, of course that will be 0.1 meters. And we're going to be using the information from the previous problem and plug that in as well for the omega, which is 0.105 radians per second. So if you take 1/10 of this, you we'll then get the centimeters cancel. You have meters per second. If you remember, the radians also are going to be eliminated. So we're going to get units of meters per second, and it'll be 0.0105 meters per second. So the tip of the second hand on the clock in the room right now is traveling at a linear velocity of 0.0105 meters per second. Question is, what happens if you double the radius? What happens if you double the radius? What happens to the velocity? Well, let's take a look. We have velocity again is equal to radius times omega. And if we double this, we're going to have 0.20 centimeters times the same angular velocity. So this is a direct relationship. If you double the radius, you will indeed 0.0210 meters per second, you will indeed double your velocity. Okay? So now what we're going to look at is going to be angular acceleration. We looked at the analogous unit of distance, which is going to be the change of the angle. It's the displacement of the angle. That's the angular displacement. Okay. We also took a look at angular velocity, and that's analogous to velocity. We now also have angular acceleration, which is analogous to acceleration. So there's going to be a third item, and it's going to be angular acceleration. Angular acceleration is going to be the Greek letter lowercase alpha. When we were looking at the omega is what's the rate of the spin, okay? And the rate of the spin is the same on any disk. If you go to a different disk, with a different spinning rate, of course, you can have a different omega there. But if you're on the same disk, you're gonna have the same omega everywhere. So the acceleration, the angular acceleration is asking how quickly is the spinning rate changing? How quickly the spinning rate is changing. So it's just like your normal acceleration. How quickly is your velocity changing per time? This is the same thing. How quickly is our spinning rate changing? So very similar to angles, where we had this is going to be our zero, and this direction is going to be the positive angle. This will be the negative angle. It's the same thing for the angular acceleration. If I am spinning in this direction and it's increasing in my spinning rate, I will have a positive angular acceleration. So that means I'm going to I'm increasing my spinning rate. Okay, you can also have, if you're spinning in this direction, you can also have a negative angular acceleration. You're still increasing your spinning rate. Okay, you're just doing it in the opposite direction. Okay, so before we do this calculation, I want to describe what the linear acceleration is.